Hello, my friends. Let's do some mathematics. Let's review the idea of induction that I introduced in the last video. I'll leave a link in the description box to that video. The first thing you have to do in an induction proof is prove the base case. Usually that's P1 for integer n equals 1. You want to prove this. It's usually easy to do. Sometimes there are many base cases. Those are more esoteric applications of induction. Maybe we'll do those in a future video. And you want to prove the induction step. If pk is true, then pk plus 1 is true. So you're assuming pk is true, and you're seeing if from this you're able to derive pk plus 1. So again, like I said last time, we're not proving the truth of pk. We're assuming pk and seeing if it gives us pk plus 1 as a consequence. Okay, so let's start with this step and look at a picture. We have all our statements lined up in order here. And let's take this induction step and draw a picture. We can think of our induction step as a little machine, kind of like a rail car, and this P1, P2, P3, and so on, that's like a railroad. Now, I would really like to attach this here somewhere, okay, because if I could do that, then knowing P4 would give me P5, right? But I can't attach it anywhere because I don't know that any of these things are true. So by itself, the induction step is insufficient to prove something, to prove the whole induction that we want to prove. It's insufficient to prove it for all n. We need a base case. So let's take a base case and let's prove something. So here, P1, suppose we did a computation and we proved P1 is true. Okay, so now we know P1 is true. Well, now we know we can latch onto something. Our little rail car can start here, you see? And because we know P1 is true, now we know P2 is true because of the induction step. So this here, let's use color, we know that this is true. But since this is true, I can move the little machine over one step. And now, you see what's going on here? Isn't this cute? Now, P3 is true. I know that P3 is true. And then I can take my little machine and move it over here. And since I know P3 is true, pk implies pk plus 1. Okay, I put k is 3. And now I know that P4 must be true. Okay, and so on and so on and so on. And my little induction rail car machine goes down this railroad and keeps going and going and going forever and ever. And then I know now that Pn is true for all, I'll write for all like this, for all natural numbers, because we began at 1 and continues to infinity. So that's the idea of induction, and the way to prove that, this is just a picture, the way to prove that induction works, one way to prove it, is to use proof by contradiction. And I did that in the previous video, so I'll leave a link to that in the box. Now, I'm going to choose applications of induction that are a bit off the wall, oddball applications. I'm sure you've seen applications to sums of numbers. Some classic one is like the sum of odd numbers. The first n odd numbers is n squared. But I'm going to do some oddball ones just to show you how wide the possible applications are for induction. So here's one. The sum of the cubes of 3 consecutive natural numbers is divisible by 9. So this is the statement Pn that I'm trying to prove. So what is n here? I'll show you. Another way I can write this is that 9 divides n cubed plus n plus 1 cubed plus n plus 2 cubed. These are three consecutive numbers here, here, and here. They start at n. So for all n in the naturals, I want to prove this statement here, Pn, that 9 divides this. All right, that's very interesting. So let's start with the base case. Base case. In this case, since I want to prove it for all naturals, the base is 1. So P1. So what does that say? 1 cubed plus 1 plus 1 cubed plus 1 plus 2 cubed. This is 1 plus 8 plus 27, and that's 9 plus 27. Oh, that's 36. And so, yes, 9 divides 36. And so, therefore, P1 is true. Notice that P1 is a statement about this. It's not a formula or it's not an equation. It's a statement that 9 divides this expression. Now, let's move on to the induction step. Okay, the induction step. So if pk is true, so we assume pk is true, then we have to try to prove pk plus 1 is true. So we have to show that pk plus 1 is a consequence of pk. So what does pk plus 1 look like? Let's look at the expression, put k plus 1 for n here. So we'll take n and we'll substitute k plus 1 for n. K plus 1 cubed plus k plus 1 cubed plus k plus 1 plus 2 cubed. Oh, that's a square, should be a cube. All right, so that's k plus 1 cubed plus k plus 2 cubed plus k plus 3 cubed. Oh, so far, good. All right, let's think about this. Okay, so if I could put a k cubed here, suppose I could put a k cubed here, then I could use pk. I could use pk and say that, yeah, 9 divides this entire thing, because these three are consecutive integers starting at k. And that pk tells us that 9 divides this. How can I do that? Well, I can expand this. So I'll do that quickly. So I expanded everything. I used Pascal's triangle to do this, 3, 3, 1, like this. And so I can quickly expand that. But look here, that's k cubed plus k plus, that's the sum of 3, the cubes of 3 consecutive integers. So by pk, since I know pk, since I hypothesize that pk is true, by pk, 9 divides this. Very good. And does 9 divide this? Yeah, because 3 times 3, that's 9k squared plus 27k plus 27. So yeah, 9 divides this. And so therefore, 9 divides this. In other words, therefore, pk plus 1 is true. So we assumed pk, and we were able to show pk plus 1 is true, knowing that. And since we have the base case, well, therefore, this is true for all natural numbers. Ta-da! Very cute proof. I like it a lot. The next application is a sum, but it's not your usual sum. It's a trigonometric sum. And I want to prove this for all natural numbers. This thing here on the right is called the Dirichlet kernel, or Dirichlet kernel, and it is of fundamental importance in the theory of Fourier analysis. So if you're into Fourier series and Fourier analysis, then this is a good thing to know. Okay, so let's start by trying to prove the base case. The base case will start at n equals 1, because natural numbers begin with 1. So the base case looks like this. When I plug in 1 for n, it looks like this. I put a question mark here because I don't know that this is true. I have to prove this. All right, so let's start proving it. I can do some fancy trigonometric transformations here. Sine x over 2, I'll add a sine x over 2, sine 3 over 2x, and I'll subtract a sine x over 2 on the other side, divided by 2 sine x over 2. Yeah, that's very interesting. So this seems to have made it worse. Now what? Well, I use this identity now, this thing. And this is one of many such identities. They have a name. We can call them sum to product rules, sum product identities. So there's many of them, there's several of them, and I chose the one that I need. Okay, so it's a sum product identity there. Okay, and I'm going to apply this where? I'm going to apply this here. That's why I chose the one that has a negative sign here. Okay, so let me expand this out now. A is this 3 over 2x, and B is this x over 2. And so let's call this, let's give this a little name here. I'll call that star for this box here. And so star is equal to this. And I'll continue this working on the brackets here. And I get this, and remarkably, this gets simpler. This is sine x over 2, and this is cos x. Wow. All right, so let's put that back into here. So we get, okay, so let's take this term here and put it back, sine x over 2 plus, now the yellow box gets simplified to sine x over 2 cos x, and this is all divided by 2 sine x over 2. Oh, very interesting. So if we now cancel this stuff out, what are we left with? Well, 1/2 plus cos x. That's very, very, very nice. I think this is like the greatest application of sum product identity I've ever seen. So, okay, great. So P1 is true. So we established P1. And now we've got to move on to the induction step now, B. Okay, I'm going to move this up. In the induction step, we assume pk is true, and we use it to derive pk plus 1. So what does pk look like? Well, I substitute k for n in my Dirichlet sum, and I have here my pk. Now, I'm assuming that this is true, and I want to see if I can get the equivalent expression for pk plus 1. So what is the equivalent expression for pk plus 1? This is my pk plus 1. How did I find this? Well, I took k and I put k plus 1. Okay, so I get the k plus 1th term here, and also this here becomes 2k plus 3 over 2 because I changed k to k plus 1. So from pk, am I able to get pk plus 1? Well, the obvious thing to do would be to add this term to both sides. So I start with pk, I start with this, and then I add to both sides cos k plus 1, like so. So I took this, all of this, here. I start with pk, and I added cos k plus 1 to x to both sides. And okay, that looks pretty good. This is the left-hand side of pk plus 1. pk plus 1, yeah, the left-hand side here. But this, what is this? Well, if I could transform this using trigonometry, if I could show that this right-hand side is the same as the right-hand side for pk plus 1, then I'm done. So what I need to do, I need to show the following. Yeah, so I need to show this. I need to take this here. Okay. I need to transform it somehow, and I need to show that it is equal to the right-hand side of pk plus 1. Then I've got pk plus 1 from pk. Okay, so this is going to require a bit of trigonometry magic. This is the expression that I need to transform. So let's start by factoring something out. I want to factor out this 2 sine x over 2. So 1 over 2 sine x over 2. This will give me sine 2k plus 1 over 2x plus, now I have to introduce this factor of 2 sine x over 2 cos, hope I have enough room, k plus 1 x. Yeah, okay. Now let's look at this here. I have here a product, and so maybe you're going to guess. The last time we used the sum product rule, but now we're going to use the product sum rule or product sum identity. It's one of many or several such identities. They're all related. And we're going to use this on this term over here. So when A is x over 2, here's A, and B is k plus 1x, the sum, A plus B, is 2k plus 3 over 2x. And the difference, what is the difference? The difference is minus 2k plus 1 over 2, all minus x. Okay, so as an exercise, so you verify this. It's really easy to do, but it's a little bit of work, and it's easy to get it wrong also. So you figure, you add these things together and make sure that it works. And so if I go back to my expression here, this is now equal to 1 over 2 sine x over 2 sine 2k plus 1 over 2. And watch this incredible magic. So I have here 2 sine 2k plus 3 over 2x. That's this one. And now this one. I can take the minus out because sine is an odd function, 2k plus 1 over 2x. And look at this beautiful magic. This cancels with this. Beautiful. And I get this. So I get this. Sine 2k plus 3 over 2x over 2 sine x over 2. But this is the right-hand side of pk plus 1 statement. And if we go back, you can verify that here. Okay, let's just go back here, this. That's pk plus 1. And so we're done. We did it. It's amazing. Amazing. It's totally amazing because this has got to be the most amazing use I've ever found for the product sum identity. Okay, and in the base case, we had the most amazing example of the sum product identity. So yeah, it's amazing. So okay, so step A of the induction and step B of the induction are proved. And so therefore, we know that Pn is true for all natural numbers. We've done it. Our little machine goes over all the natural numbers. Well, there we have it. Some very nice examples of induction. I'm going to do one more video, I think, on induction and choose some more oddball examples and do them. It's very interesting. I like induction very much. I hope you enjoyed it. If you've ever had an interesting use for those product sum identities why don't you leave a comment in the description box? I vaguely remember a long time ago when I first learned those identities, someone told me that they're named after some famous guy like Tycho or Kepler or something like that. I don't know if that's true. Like maybe you know, if you know the story behind who those identities are named after, please leave that in the comments. I would like to know. Okay, I will see you next time.